Before we design a structure, we have to understand how forces will affect the material. This understanding will allow us to either understand how the material can fail in service and what might go wrong, but also to be able to select the right mechanical testing so that we can assess the performance of things like our welds and our material selection to meet the desired purpose. In this video, we're going to go through the 4 main forces and ways that those forces are applied, as well as some examples of the mechanical testing which can be used to assess those forces. So the first material properties we'll look at here is strength. So the pure definition of it is the ability of a material to resist the application of force without a failure. And a really good example of this is a tensile test. Now, in a tensile test, what we're going to have is a part, and we're going to apply a stress to that, in this case, a tensile stress. And as we pull that tensile stress, that part apart, we're going to map a graph very much like the one on the right here. And in this graph, what we can see is we get a yield point, which is RE. RM is our ultimate tensile strength, or our UTS. Now we can work that out with the equations we've already talked about in one of our other videos, which I'll link above. Now you can see around the yield point, it kind of jumps around. Here we have a yield higher and a yield lower limit. And that just gives us the window in which yield is kind of given and not. But we take an average of that, which is our RE. Now, in that tensile strength, we said we can cover UTS, ultimate tensile strength, yield, and elongation. In our elongation, again, within the other video, we show how we work that out, but it's 2 very distinct points on the test sample we're going to measure, with UTS and yield coming from the graph. And those UTS and yield are going to help us see the strength of the material. Now we take that information, and in steel, we'd normally apply a 2/3 limit to the yield point in order to get our safe working zone. 2/3 yield is a very common assumption for steels, and keeps us well away from the point at which we get plastic deformation at the yield point within the component, because that wouldn't be useful to very many of our applications, unless you're doing something like steel pulling, wire forming, stuff like that. Our next one we're going to talk about is toughness. So this is the ability for a material to resist crack growth, normally under an applied force. And again, our example here is going to be Sharpie V-notch tests. And in this test, what we're going to do is take a bar, machined across our weld, and then normally 10 by 10 by 55 millimeters long. We can get smaller. This vertical 10 millimeter limit can be 7.5, 5 and 2 millimeters. But the 10 millimeters by 10 millimeters gives us fairly consistent results. As you make sub-size samples, you can see the results be a little bit scattered. So in the middle of that sample, what we're going to do is machine a notch, and that's going to help us have a point at which we can create the crack growth in a place where we can measure it and it's useful to us. So next we're going to take our sample with the produced notch within it and stick it into a hammer and anvil type situation where they're at a temperature, and then we're going to hit the piece and it'll break. Now what we do is we have multiple samples and we plot the results at temperature and the energy absorbed within the test, and we get something that looks a bit like this where we plot a line through. And what we can see with this is we can say, okay, well, at minus 30, what is the energy absorbed? Are we starting to get brittle failure, or can we get the temperature up enough to have enough energy absorbed for our design criteria to have ductile failure? So this graph can be split into a ductile area and a brittle area. And that section, that near vertical line that appears between them, is what we call our transition temperature, from where we go from having toughness, which has ductile failure, to a brittle failure, which we don't really want. Our next one, hardness. So this is the ability of a material to withstand or resist indentation. So a good example of this is hardness testing. So here we're going to take our diamond indenter, and I'm going to talk about Vickers hardness testing here. There are a couple of other types, there's Brunel and Rockwell, but overall, for me, I think for a lot of people, it's quite a common test now, is that a diamond pyramid indenter, when compared to a ball type indenter within the other tests, especially at higher hardness values, doesn't deform as much, so the results are a lot more accurate. So Vickers tests are very, very common. So what we're going to do here is, under a load, apply that indenter into the surface of the material, and then we're going to take the indenter away. And we can do this load, the common ones are 1 kilogram, 5 kilograms and 10 kilograms. You can get, really any loading you want, but it's definitely specification dependent. And what we're going to do here is, once we've applied that load and we have the indenter, is look down at the surface of our indentation, and we use, through a microscope, some slides which allow us to move in and measure the size of that indenter. Then, because we know the load we applied and we know the surface area, because we can measure it, we can calculate the hardness through load over the surface area of our indent, and that will give us a result. Hardness is a good thing to understand because it links very nicely with brittle failure. If we have a risk of brittle failure, it's normally in higher hardness materials. So we can understand our mechanical properties and the risk of failure coming out the back of those mechanical properties. And our last one here is malleability. So malleability ties in very much, is how much can we bend or deform a component. And a good example of this sort of test is a bend test. If something is malleable, it will bend more easily without failure. So here's a very simple 3-point bend setup. And our former size here is normally around 4T. So the diameter of our former is 4 times the thickness of the material we're going to bend. And what we do is we push them down and form our material around. And in this case, we have our face in tension and our root in compression. So we would be testing the face side of the weld. And this would, check malleability. Would also check for if we have any lack of sidewall fusion defects, which will allow that face to be ripped apart because of a welding defect. And of course, if we rotate this round and bend it the other way and put the face into compression and the root in tension, we get the same effect, just now we're testing the root, not the face. Now, the selection, whether we have a face or a root bend or a side bend, which is the same test just across its cross-sectional area, is this sort of magic number here of 12 millimeters for British standards. So anything up to 12 millimeters, we would do roots and face bends. Anything over 12 millimeters, we do a side bend. It makes it easier to do the test, because once we get to big, large thicknesses, then it's quite difficult to get the samples to bend. And then as our summary and our overview, there's the 4 main mechanical properties you would need to know as a welding inspector. Toughness, looking at the ability of material at low temperatures. Hardness, how likely it is to crack. Strength, does the material have the pure strength in itself to say, be able to take its own static weight? And malleability, will it deform in a way without rupturing? So that's the end of our video today, and I hope that's useful in your studies. Mechanical properties are a very good thing to understand early within your studies, as it does link into a lot of the things like hydrogen cracking and those types of failures. That's us for today, so thank you very much.